All right, guys. So we just saw a little while ago that when it came to dealing with sinusoidal sources and phasor transforms, we could talk about the IV characteristics of a resistor, a capacitor, and inductor in a very similar manner, as long as we generalize the concept of resistance and define what we called an impedance. So right now, I want to spend just a little bit of time talking in a little bit more detail about impedance as well as some of the components that you will see within the impedance, as well as another concept called the admittance, which is the inverse of the impedance, as well as the components that it may contain. So there's going to be a lot of terminology and a lot of definitions, but they will serve you well as you go through your electrical engineering education. So let's go ahead and start talking about impedance and admittance. Now, impedance itself, we use the capital letter Z to denote it. And depending on whether you were talking about a resistor, inductor, or capacitor, this quantity could be purely real or it could be purely imaginary. And in general, impedance is a complex number. Because it's a complex number, that means that in Cartesian form, it can be rewritten as the real part, which we're going to call R, plus J times the imaginary part, which we're actually going to call X. Now, in terms of the components that we actually have here, this right here is the resistance, while this component here, this X, apart from the J, goes by another name. This is what they call the reactance. Now, keep in mind that for uh, resistors, capacitors, and inductors, resistors don't have a reactance. They only have the resistance, so it's always purely real. But the reactance, depending on whether you're talking about a capacitor or an inductor, is calculated differently depending on the frequency of the input signal. In particular, for a inductor, the reactance of the inductor, and I'm using a lowercase l as a subscript L here to remind you that it's for an inductor. Well, it depends on its angular frequency and its inductance, like so. Notice that the J itself has not been included there. While for a capacitor, it has no real part when it comes to the impedance. It does, however, have a reactance, and the reactance of a capacitor is minus 1 over omega c like this. So I really wanted to kind of bookkeep and keep these terms clear. So far, we really have three terms here when it comes to impedance that we need to define very carefully. Now, we also have another definition that becomes quite useful depending on what the application is, and that happens to be the admittance. The admittance, we use the capital letter Y to denote it, and by definition, it is 1 over the impedance of the circuit, right? Now, since the impedance is a complex number, the admittance by its very nature is actually going to be complex as well. And if we rewrite it in Cartesian coordinates, it can be rewritten as the real part of the admittance plus J times the imaginary part of the admittance, right? So this is the admittance. Let's actually write that a little bit more cleanly. It's a little bit harder to see. So this is the admittance. Oh, I'm struggling to write this out, so bear with me. This right here is what they call the conductance, And lastly, the B is what they call the susceptance. Right. Keep in mind that the units here for all three of these, admittance, conductance, and susceptance, they all have the same units. They're the inverse of ohms, which also goes by another name. So the unit of admittance, the unit of conductance, and even the unit of susceptance is 1 over an ohm. This goes by either the name mho, which we use the upside down Greek letter omega to denote, or it also goes by the name Siemens, which we use the capital S to denote. And again, we will see instances in which it's more convenient to actually use things like admittances rather than impedances. One last thing worth noting is there are ways in which you can actually calculate, for example, resistances, reactances, conductances, and susceptances if you actually have the other. I'm going to go ahead and state these without proof, so there's some useful relationships here that may be worth writing down. So these are some useful relations. First is if you happen to have the conductance and susceptance, then the resistance is G divided by G squared plus B squared. Similarly, the reactance is B divided by G squared plus B squared. And the inverse transformations are V is equal to R divided by R squared plus X squared. And lastly, B is equal to X divided by R squared plus X squared. It should be a relatively simple matter to calculate these relationships if you actually use some complex algebra here and a little bit of trigonometry. This is all I have for you guys for this section. Uh, and again, these are definitions that will serve you well. So it's a good idea to keep these memorized.